Hi folks, I'm Stephen Heumann, and today I'm going to be presenting what's new in ORCA C. So first of all, what is ORCA C? As many of you probably know, it's a C compiler for the Apple IIGS that was written by Mike Westerfield of the ByteWorks. And more specifically, it's the only C compiler on the Apple IIGS that complies with the national and international C language standards, which is something I'll talk a little bit more about later. And it's also one of the ORCA family of languages, which means it runs under the ORCA shell, which is a textual shell environment, and also has a graphical IDE-like environment that you can use if you want. And in addition to that, it can integrate with other ORCA languages like the ORCA-M assembler and the ORCA Pascal compiler. So now to go into a little of the history of ORCA C. ORCA C 1.0 was released back in 1989. There were several updates in the years following that, culminating in ORCA C 2.1, released in 1996. Then in 2000, the ByteWorks put out a collection called Opus 2, which was basically all their Apple II software, including ORCA C, in one collection. And with that, they also made available the source code for their software, including ORCA C. So that meant that people could get that source code and look at it and potentially start modifying it. And that's what I did, initially kind of fixing bugs and then starting to add some new features. And in 2017, I asked Mike Westerfield if I could put that source code up publicly and start making some new releases containing my improvements. And he allowed me to do that by posting the source code on GitHub. And so for the last several years since then, I've been putting out several ORCA C 2.2.0 beta versions, containing my bug fixes and enhancements progressively through those versions. And that brings us to today, when I'm announcing the ORCA C 2.2.0 final release. So in the rest of this talk, I'll be presenting ORCA C 2.2 and talking about what's new between ORCA C 2.1, the previous commercial release, and the 2.2 version. So ORCA C 2.2 adds almost all the features that are required by the latest C language standard, which is something I'll talk a little bit more about later. It also has some other features like improved error checking and some other miscellaneous improvements, and it's got many bug fixes. So first I'll just talk briefly about the bug fixes. There have actually been over 250 bugs fixed between ORCA C 2.1 and 2.2. And these are all kinds of things. They're code generation bugs, where it would generate the wrong code, sometimes specific to using certain optimizations. There are issues where it didn't quite conform to the C language standards. There are bugs in library functions, just generally all kinds of things. And I won't spend too much more time talking about these, but they really are an important aspect of what's new in the release. And I think if you've encountered bugs in previous ORCA C versions, there's a pretty good chance they've been fixed, so I'd encourage you to try the new one. Now I'll talk briefly about the C standards so we can understand kind of how ORCA C complied with standards and what the newer standards are that it's now using. So to talk briefly about the history of C, it was developed back in the 1970s at Bell Labs, but initially there wasn't a formal standard from a standards body for it. Then in the 1980s, there was an effort to develop a standard, which was initially done by the American National Standards Institute. And they published a standard in 1989, so it's called C89 or ANSI-C for the American National Standards Institute. And then in 1990, essentially the same language standard, just reworded a little, was adopted as an international standard by ISO. So that version is called C90, but C89 or C90 are essentially the same language. Then that was followed up in 1999 by the C99 standard, which added quite a few new features to the language. And then it was followed up again in 2011 by C11, which added not quite as many as C99, but still a number of new features. And then finally C17 in 2017, which did not add any new features, but it did make various clarifications and corrections to the standard document. So to show how that relates to C compilers on the 2GS, The first C compiler early in the history of the 2GS was APWC, released by Apple, although it was developed by a third party. And that was a pre-standard C compiler that didn't have various of the features that the later C standards would have. And so that brings us to ORCA C, which the original releases from that, from 1.0 through 2.1, were complying with that initial ANSI C or C89 or C90, that first generation of C standard. But ORCA C 2.2 updates that all the way to C17, the latest standard as of this time. And I'll point out briefly, there's also an upcoming standard that's in development and actually pretty close to done, which gets referred to as C23, although it now looks like the official publication of the standard will probably be in 2024. So ORCA C doesn't support that yet, but that's something I'll talk a little bit more about as a direction for the future. So now to briefly go over the new language features that have been added in these newer standards and that ORCA C now supports. First, I'll talk about some C99 features. One of the big ones is that you can now mix declarations and statements within a block. Previously, in a block with curly braces, like the whole body of a function or a block within it, any declarations had to come before any statements. So you couldn't mix them freely in the block. But as of C99, you can do that. So you can have declarations that come after statements, and they can be intermixed any way you want. And kind of related to that, you can also have declarations in the first clause of a for loop. So for example, you can see in this example here, we define the loop control variable int I right in that first clause of the for loop, whereas previously you would have had to declare it before the for loop. And another class of new features in C99 is that it adds some new types. And probably the most significant one is that it adds integer types that are at least 64-bit. On most implementations, including ORCA C, they're actually exactly 64-bit, called long, and for the unsigned version, unsigned long. And in addition to that, there is also a Boolean type called bool. So that those 64-bit integer types allow you to represent bigger integers than would have been supported previously, and the Boolean type represents Boolean values, so true or false. Some other things that have been added in C99, there's a new hexadecimal format that you can use to represent floating point constants. So the integer and fraction part are represented in hexadecimal, and then the exponent is represented as a power of 2. There's also compound literals, which are a new form of expression that you can use to essentially declare an unnamed variable, initialize it, and then refer to it all as one expression. So for example, if you want to have this rect, which is a kind of structure that comes up in the 2GS toolbox, and you want to use that somewhere, like maybe you're passing it to a function, you can just declare it as an expression, and parentheses rect as the type, and then the initializer for it, and just use it right as an expression without having to declare a separate variable for it. Another significant C99 feature is designated initializers. So these are initializers for structures or unions or arrays where you're explicitly declaring which element of them is being initialized. So for example, here you have a point P, and the .v element of that, the vertical coordinate, is initialized to 10, and the .h is initialized to 20 for the horizontal coordinate. And that just allows you to explicitly see which elements you're initializing, and also it means they don't have to be in order. And you can actually see that in the other example for initializing an array, where you initialize element 1, then element 0, then element 2. So as you can see, they aren't going in order. And those are just some of the C99 features. Obviously, there are a number of others that I don't have time to get into here. And then moving on to C11, that has even more new features. One of them is that there are now Unicode character constants and string literals that can be used to represent characters and strings in the various Unicode encodings, which can be useful for interchanging data with modern systems that are likely to use Unicode. Another thing is that it now supports static assertions, where it can statically evaluate an expression and assert that it should evaluate to non-zero. And if it evaluates to 0, then that will be considered an error, and the compiler will print an error message and stop compiling. So for example, in this case, we can check that the size of the int type is what we expect it to be. Another C11 feature is that there's now a no return function specifier that's just used to explicitly declare that a function does not return to its caller. And again, these are just some of the features. There are more that I don't have time to get into here. And finally, there are actually a few features from that upcoming C23 standard that ORCA C already supports. It doesn't support most of C23, but it supports these couple little things. So one of them is binary constants, where you have a number prefixed by 0b and then binary digits. So that just allows you to represent a number in binary, which can be a nice thing to do, for example, and it's actually representing in some set of bit flags or something like that. And another is the hash warning preprocessor directive, which just allows you to make the compiler print out a warning message when it's compiling something, but not actually stop compiling it, which you can just use that kind of in preprocessor directives if there's maybe something that's not quite right and you want to print out a warning about it. So now I will get into some new library features that are supported. One of the significant ones is that there's some additions to the printf and scanf, the formatted output and input functions. And one of the big ones is additional length modifiers for various types. So you have now LL for long or unsigned long, which, as I mentioned, are those 64-bit integer types that have been added. There are also now explicit length modifiers for signed or unsigned char, for size t, pointer diff t, int max t. So this just allows you to conveniently print or scan in any of those types. Another thing that's been added is that it can print out or scan in floating point numbers in that kind of hexadecimal floating point format that I mentioned earlier. So you can use that in source code and also use it with printf and scanf. Another thing that's been added is the snprintf function. So you can print to a string buffer, but limit the size of the buffer so you don't overflow it. And again, there are some other additions that I don't have time to get into here. In addition to that, there's been a bunch of new math functions that were added in C99 that are now supported. I don't have time to get into what all these do, but there's quite a bunch of them. So if you are interested in writing mathematical code, you can look into these, and quite possibly some of them would be useful to you. And finally, there's kind of a grab bag of other additions to the library. One also related to the mathematical stuff is that there's now a floating point environment support. So you can configure the rounding mode, like round up or round down or round to nearest or round to 0 for floating point operations. And you can also look at the floating point exception flags. So when floating point operations encounter errors, like for example overflows or underflows, they set exception flags, and you can now look at those to check for those kind of errors. Another function that's been added is stirf time, which is a time and date formatting function. So that allows you to use a format string to indicate what format you want a time and date to be represented in, and then it can write it out in that format. So it's flexible for representing various different time and date formats. And also related to time and date, we can now use the time toolset by Jeff Weiss, if you have that installed and you set some options to enable it, to handle time zones, which is something that the library previously couldn't do because the built-in Apple IIGS system software doesn't really keep track of the time zone. In addition to that, there are math functions operating on the new long type. There are Unicode conversion functions that can convert between the 2GS desktop character set and Unicode using UTF-16 or 32. And there's a new header called studint.each, which defines a bunch of fixed size integer types, for example, int32_t. And types like that, for example, is just always a signed 32-bit integer type. So that allows you to have a type of a specific size without needing to worry about variations between platforms. Like, for example, on the 2GS, the basic type int is 16 bits, whereas on most modern platforms it's 32 bits. And so with the basic types, you can get variations like that, but by using these types declared in student.h, you'll always get a fixed size regardless of the platform. And again, these are just some of the additions. I don't have time to get into everything here. So now briefly what's not supported. Really the only major feature from C11 or C17 that is not supported is wide characters using the wchar_t type. And that's a type that's designed to represent characters using some broader character set than a basic 7-bit or 8-bit character set. In practice, it's usually Unicode, but the 2GS has no real convention for representing wide characters, so that is not supported in ORCA-C. Apart from that, there are a number of features that are defined in the standards but made optional to implement or not, and so ORCA-C also chooses not to implement those. And these are things like complex numbers, variable length arrays, multi-threading, and atomics. And I should point out, complex numbers and variable length arrays were actually mandatory features in C99, but then they were made optional in C11. So ORCA-C is focused on the latest standards like C11 and C17, so it chooses to treat them as optional and not implement them. Now I'll talk briefly about some new features in the compiler that aren't directly tied to what's specified in the new standards. And maybe the biggest one is some additions to pragma_lint. So pragma_lint is a directive you can use to make ORCA-C check for some things that aren't necessarily detected as errors by default, but really are likely to be errors or something you don't intend in your code. So one of the big ones there is that it can now do printf and scanf format checking. So that means when you use those formatted input-output functions, it will look at the format string you specify and then compare that to the number and type of arguments you give to the function and make sure they actually match. Because if you don't, that will essentially be an error and not behave correctly whenever that function is called. And I should point out, this is actually something that was contributed by Kelvin Sherlock, so thank you to him for that. Some other pragma_lint checks that have been added is for undefined behavior in computations. Things like integer overflow, invalid shift counts, division by 0, in cases where they can be detected at compile time, like when you're operating on constants. Another thing is implicit conversions that change the value of a constant. For example, when you have a constant value and you assign it to a type that's too small to hold that value, it can give you a warning about that. Another thing it can do is give you an error about syntax disallowed by C99. So the C99 standard disallowed some things that previous C standards allowed. And by default, those are still allowed in ORCA-C to maintain compatibility with older code. But by using this pragma_lint directive, you can get an error for those things that are no longer allowed in the current standards. And finally, there's a couple additional ones for functions that don't return a value. For example, executing to the end of a function that's supposed to return a value but actually doesn't. And for variables that are just never used in your code. And apart from pragma_lint, there are some other additions and features in the compiler. One of them is just improvements to the generated code. There generally aren't huge improvements there, but there are some improvements here and there, so you'll usually get at least a little better code in a large program. And finally, some internal size limits have been raised to allow you to compile larger programs. There is better detection of some classes of errors. Apart from just that pragma_lint, there are some things that are unambiguously errors that were missed before but are now detected. And there's also a way to select what C standard you want to use. So you can select either a strict conformance mode to one standard or kind of a more permissive compatibility mode for multiple standards. And now moving on, I'd like to briefly show you an example of ORCA-C in action. So we'll go over to the 2GS emulator here, and we have a little program that's supposed to compute a factorial. So in this case, it's computing 20 factorial, which is just 20 times 19 times 18, etc., down to times 1. And so it's got a loop to do that. And that also has a version of that that will actually be computed at compile time, and it compares the two and see if they match. And if you look at this, you can see it's using several of the new features. So for example, it's using the long 64-bit integer type, which is actually necessary because the other integer types would not be large enough to fit the value that we're going to be computing. Another thing is we declare the loop control variable within the loop here, int I equals 20, declared in the loop. We also have a declaration here for this expected variable that comes after the statements, like the for loop and the printf. So this is an example of mixing declarations and statements, which again is something new in C99 and later. So let's go ahead and try to compile and run this program. So we say compile to memory, and we can go over and look at the shell window, and you can see it compiled successfully and ran, but it didn't quite run correctly. It computed 20 factorial as 0, which is not right. It should be some large number, not 0. And it also says the computed value does not match the expected result. So now let's add in that pragma-lint directive and see if that can help us debug it. So we add that in here. We say pragma-lint -1, which means enable all the lint checks. And now we'll do it again. And it says lint invalid format string or argument. So that is the printf format checking I mentioned earlier. And it points right here to the printf statement that I was talking about. And in this case, the issue is that we need to use the LL length modifier because we're printing this val variable, which is of type long. So we modify that and compile it again. And it's now saying lint integer overflow in expression. It points us to right here. And what this is saying is this, as it's computing this 20 times 19 times 18 times 17, that's actually going to overflow. And the reason for that is that all these variables are of type int by default, because an integer that fits in a type int is int by default. But that's not what we want here. We want the computation to be done in type long, which will allow us to represent larger numbers. So we can do that by adding this LL length modifier on the first number here, the 20, and that will wind up causing the whole computation to be done with type long. So now we do that, we compile it again, and we can see it compiled and ran successfully. It computed 20 factorial as this large number here, which is correct, and it matches the expected result. So that's just kind of an example of some of the new features you can use in terms of language features and in terms of these debugging features with pragma-lint. So now, how do you get ORCA C E2.2? Well, if you already have ORCA C 2.1, then it's available as a free upgrade that you can download from the GitHub site for ORCA C, which is linked right there. If you don't have ORCA C, or don't have ORCA C 2.1, then you can get it as part of Opus 2, which is that collection of ByteWorks software that's now sold by Juice.js. And as of right now, the existing Opus 2 collection contains ORCA C 2.1, so you'll need to get that and then apply the update to ORCA C 2.2. But coming, hopefully sometime pretty soon, should be an update to Opus 2 that has ORCA C 2.2 directly integrated into it. So keep an eye on Juice.js for that. And finally, to talk briefly about future plans for ORCA C, I do intend to keep developing it. The main future plan I have at the moment is to work toward implementing the features from that upcoming C23 standard, which I do intend to do, although it's a pretty big update, so it'll probably be a few years before I have all of that implemented. Apart from that, I'll look to incrementally improve the performance of the generated code, keep fixing bugs, and try to respond to feature requests from users. And so I would welcome feature requests. I'd also welcome any code contributions that people want to make. It's on GitHub, as you can see right there, and people are welcome to contribute to it. And so that will conclude my presentation, and thank you for watching, and I'll be happy to take questions now or anytime on the Discord. I've seen some questions on the Discord, so I'll go ahead and answer those.
Great.
One was asking kind of what's the utility of the hexadecimal floating point format. Basically, the internal binary representation of floating point is using a binary-based format, and the hexadecimal corresponds pretty much directly to that. whereas with the traditional decimal representation of it, you can get some conversion issues. So you might have kind of a rounding error going between hexadecimal and decimal. So that's just kind of a more direct way to represent what it actually is internally. Another thing I was asking is about the strl copy function. That is not in there because it's not part of the current C standards. There are a number of useful functions that could be implemented. I've mostly chosen to stick pretty closely to the C standards. There's actually somebody pointing out here, it will be in the upcoming POSIX standards. Some of the other things are in POSIX, but not the C standards. Some of those things like that could potentially be implemented in the future if people are interested. That can also be done as a separate library if people want to, or if you find open source code online implementing those functions. For the most part, it will work pretty easily in ORCA C. Another thing I'm seeing people talking about is the year 2038 bug, where the time representation runs out of bits and can't represent the dates anymore. ORCA C actually uses a unsigned 32-bit time representation, which is different. Year 2038 bug is primarily for signed 32-bit time representation. So time in the ORCA C libraries actually can represent up to 2105, but not beyond that. Although there may be some issues, some other places of GSOS will kind of run out earlier. So there may need to be some patches for that. But ORCA C can represent up to 2105. Now, it does now support the 64-bit integer types. So beyond that, that could be changed over to use the 64-bit types, and then it would represent some huge amount of time. But we haven't done that so far. I'm seeing a question about levels of optimization. How efficient is the generated code? I'd say it's okay generally, but not great. I know people have opinions about this. There are things that are a little better in the new version than the old version, but mostly not too dramatically. So it's not going to be as good as hand-generated assembly, but I think it's good enough for a lot of things. Asking in mixing 6502 or 65C16 assembly. Yes, there's a mini assembly built into it, so you can have assembly code directly within your C program. So that would normally be 65.816 assembly. Normally, you probably wouldn't want to try to go into 6502 emulation mode within ORCA C code.
One that showed up in there was, is there an internal representation that the optimizer is using?
Yes, there is an internal representation that the optimizer is using. It's actually similar to P code, if you know what that is. Some optimizer passes are working on that P code. Some of the optimizer passes are actually working basically on the assembly code. So there's a mix of stuff, but there is an internal representation there that gets optimized. And that is something that could be improved. Essentially, if you kind of look at all your standard optimization algorithms in compiler textbooks, most of those could be applied to that internal representation. That's a fair amount of work to do and get it right. There might be performance issues doing that on the GS, but that's something that we can potentially look at in the future. I might do that. I'd certainly welcome contributions from others as well. I see, what's the typical workflow with ORCA C? Do you write stuff on the GS, maybe in an emulator? Yeah, this is something I should point out. You can obviously write it directly on a GS. It runs on a real GS. You can use a traditional GS emulator. There's also something called Golden Gate by Kelvin Sherlock, which is a separate product that you can buy from Juice GS. That essentially is kind of a specialized emulator thing, but it essentially allows you to run ORCA C or the other ORCA languages as cross compilers on a modern computer, which will obviously be very fast. So that's a good option for people looking for that. Asking about ORCA Pascal bugs. I haven't fixed anything in ORCA Pascal. Essentially, there aren't new Pascal language standards coming out, so there isn't quite the same impetus to do updates there. I'm aware of a few bugs in the ORCA Pascal compiler, but nothing too bad. So that's something I or others could potentially look at doing in the future.